Hi everyone, David Mala here. Today I got some really cool stuff we're going to be doing. So today we're going to be working with a really cool data set. This is the Baltimore water quality data set, which shows 5 months of data from 2018. Some days were good quality, some days were bad. We're going to delve more into the lead parts per billion or lead composition levels of the water. But in this data set, there's all kinds of stuff. There's arsenic levels and other things. But for today, I want to show you how we can use that to forecast and see, what can we see with it. So if you look right here on my screen right here, you have 4 different graphs, right? And you have 4 different forecasts. We're going to go through from beginning to end and show you how to do each one of these and compare them and come out with which one is the best. So I'm not going to tell you which one's the best right now. I'm going to let you think about that one and look at that a little bit. But let's go into the actual data here. So let's look into our code and our data. So let's open this up and shrink these graphs on down so you can see everything here. I want you to see everything. All right, so first we're going to start off with, we got 3 libraries we're bringing in: Tidyverse, ReadXL, and Forecast. ReadXL because we're going to bring it from an Excel sheet. Forecast because it's got some process we're going to use later on, I'm going to show you, and Tidyverse for various little pieces we do in here with ggplot and things like that. So first what we're going to do is and I've got every piece of code commented here so you can see what it is. So the first one is right here. We're going to load in our data set. Our data set is the Baltimore, Maryland water quality data set. I will post this up on Kaggle, and I'll give you a link to it down below as I get to it. Let me finish this video first. And anyway, so it says load the Baltimore water quality data set, 5 months of data from 2018. So we load that up with ReadXLSX, which is a function of ReadXL, and we put that in this data frame called water data set, right? Next, we have 10 locations in that data set. So if I were to look at that, okay, here's our data set, right? And we have locations 1 through 10. On each day, there's 10 different locations they did this with. And as I told you earlier, there's lead parts per billion, copper parts per billion, pH, fluoride levels, volatile solids, total solids, cryptosporidium, which is something you definitely don't want in your water, arsenic, and your basic water quality and fail reason. Did it pass? Was it in water quality? Did it not? Did it fail? And what reason did it fail for? Did it fail because of cryptosporidium? Did it fail because of total solids? What did it fail for? That's all in here. Well, today we're not going to go into the actual whether it passed or not. We're actually going to go into this lead ppb, parts per billion. And what we're going to do is we're going to forecast that out to see, can we see what our lead levels will be in the future, what they should be with high accuracy. I don't want to deal with stuff where we have low accuracy and we're just flipping a coin. Might as well just flip a coin. No, we want to see this with very high accuracy. I want something that's 90%, 89%, 95%, somewhere in that range of accuracy. All right, so let's get back to our data here. We've loaded it in, right? Next what we're going to do is we're going to filter it to that location. As I just showed you, there's 10 locations. You cannot go and forecast all 10 locations at the same time. It would make a very big mess. So what we want to do is we want to look at one location. So we're using this right here, this piece of code right here, which is water data set, and this is with your arrow, right? This is how you pipe in R, 2% signs with a little arrow inside, which is your greater than sign symbol. Filter and location number equals 1. If you just put equals 1, it'll give you an error and say you needed to have equals, okay? So instead of putting it back to water data set, I want to put it to a new one. So that way I can always quickly go back to my data and bring it back in if something gets messed up, the graph gets wrong, something goes wrong later on. I can quickly, instead of going back and loading the data back in, I've got steps that I only have to go back 1 or 2 steps instead. So water data set 1 is the new data set filtered to location 1. Next what we're going to do is let's take a look at our data right off the bat, right? So we're going to use ggplot. ggplot of water data set with aesthetics, that's what AES is. X equals the date, and Y equals lead ppb, right? That's what I told you, we're going to focus on lead, okay? And so let's run this and see what this does. Boom. Oh, that looks really nasty, right? Now, that was the full, see that was water data set? That was the full one before I went and filtered it to 1. Remember that? So this is why I want to filter to 1. That's got all 10 locations in there. It looks really nasty. So instead, let's do the next one right here, which is the same thing, but I changed water data set to water data set 1, where you've got it filtered to 1. That looks a whole lot better, right? That's better than the other one was by a long shot. Now, let's take that original data set and aggregate it by the mean for each date, right? So let's take a look at this. We got kind of the same kind of concept, except now we've got ggplot of water data set plus the stat summary aesthetics of the x equals date, y equals lead ppb like before, but we've got the fun.y equals function x of length x, and that is divided by the length of unique x. That gives us the mean, and geom equals line. So it sounds like a lot, but it's really not. You're just basically, this stays the same for anything you're trying to do a mean on like that. The rest of it's just your typical stuff you did before of the x equals date, y equals lead, ppb. And so if you run this, look at the difference. That looks a little bit better, right? So now we can see how our levels, where they are, they tend to range between 1 and 1.5, except we have one outlier there in September. Alright, so next what we're going to do is we're going to look at one variable we're interested in forecasting, right? Lead levels, right? So let's do this. And we're going to take that and we're putting that, so now remember before the data set had arsenic levels and all these other things, volatile solids, and whether it passed or failed and why and all these things. So we're just taking it down to we just want lead, right? So see this right here, I'm taking the lead ppb, which is that column, right? This is that data frame, water data set 1, lead ppb with $sign here, right? And I'm putting that into water data set 2, right? So I'm not going back to water data set 1 right now. So let's do that. You're not going to see anything over here. That just does it. And so now we got that in water data set 2. Now let's take that, and what we're going to do is going to plot a time series. Okay, so remember, we can't forecast without that. We need to have a time series. Time series means we're going to use the time series function TS, right? So as you can see right here, I clearly have frequency equals 365 because this is daily data. If you look at it, it's every day. So it doesn't matter how many weeks you have. You got daily data, you want to have 365. Okay, for your frequency. Now, start date is the month of 7, which is July of 2018. So that's where we start, and then the end is 11 of 2018. We don't need to put the end date, so we just put TS water data set 2 start equals C 2018 comma 7 frequency equals 365. You put that into T series 1. Then we go and print it and plot it. Print and plot. Look at the difference here. So print gives you this, plot gives you this. Okay, so it sounds like you're saying the same thing, print, plot. They're not the same thing. Print means I'm printing all of my frequencies right here on the bottom part right here. See that right there? That is our time series forecast and stuff. And then over here we have everything in a time series. And then over here we have our actual plot of that. Okay. Now, the reason why it's small and not big is I have these things over here that I'm going to use in a minute, and they're called par and froze. What this does is it parameterizes the frame of the plot area. So let's take this, put this up here. Where we just were is right, what do? We just did plot, right here. So if we do this instead right here, and right before the plot, we can do this because it doesn't matter if we do it up above it, but let's just do it right here. So we do this and we say 1 comma 1, right? So we just set it to have one graph instead of the 4 that you saw here earlier. That's why it was split up this way, so you could have 1, 2, 3, 4. So if we do this, let's grab this right here. Now watch what happens. There you go. It's just bigger, that's all. Basically you can see that much easier. It's still a little bit messy looking. Okay, so now let's do the same thing. I just want to show you, what if I did the plot.ts? Some people like to use that. Okay, that's this. Instead of plot, plot.ts of T series 1, right? So let's do this. Same thing. See, no change. It doesn't matter which you use, okay? Use one or the other. It doesn't matter. Now, let's remove the outliers and extraneous info in here, right? If there were anything missing, we want to fill it with the mean. And that's what this does right here. We use TS clean as the function right here. and it's TS clean of T series 1, which is our data, our time series data. Replace dot missing equals true, lambda equals null. That's all you need to know for that. And what that does, it's going to put that into right here into water data set 1 of $clean lead ppb. So this is the clean, so I could use that as my clean column, right? If I had a dirty column, now I've got a clean data column. Okay, that's how that works. Now let's plot the clean data with ggplot. Let's plot this nicely. So we got ggplot plus geom line, data equals water data set 1, aesthetics, and notice how instead of having just lead underscore ppb, I now have clean lead underscore ppb. That's the column for that. So let's do that. Let's see what we got. Oh, there we go. So that's the clean. It's the same thing because there really wasn't any missing data here, but I'm showing you that step because what if you did? You want to always be prepared for what if. You know, you can't depend on, well, I'm never going to have bad data. Yes, you are. As a data scientist, you're going to have a lot of bad data, a lot of erroneous data, a lot of missing data. So you need to know how to be able to handle that. Now, let's go to the centered moving averages, because when you're doing this, you want to have centered moving averages. There's a reason for it. If you did a leading moving average, you would be biased towards the front. If you do a trailing moving average, you'd be biased towards the back. A centered moving average moves in the middle, and it takes from both ends equally. So it's a better, more accurate measurement to use. So we're going to do it for both a period of 7 and a period of 30. Okay, so see this right here? What we're doing is equals MA, moving average, of the water data set 1, clean lead, remember we're dealing with the clean column, okay? Order equals 7, and then we got one right below it for order equals 30. And we're putting the one where it's order equals 7, which is a week's data, right, is going into weekly, and the 30 is going to monthly, okay? So let's run that. Boom. All right, next, plot the moving averages with ggplot. So let's take this, and I'm going to show, now it's ggplot plus geom line for each one. See, there's a plus at the end for all 3 lines, right? And we've got the color equals clean lead ppb levels, weekly moving average, and monthly moving average, right? So let's do this. Give it a second. There it is. Let's bring this up bigger so you can see what we just did. What we just did is I'm showing you the red is just the clean data coming in, the green is the monthly, and the blue is the weekly. So if you look at the blue, see how it stops after the red? That's because it's removing the front and does the same thing over here at the back of 3.5 weeks. Remember, it's 7 weeks is what we did. So 3.5 weeks in the front, 3.5 weeks in the back are off, right? And the same thing with the monthly moving average. Okay, the monthly moving average, except that it has 30 days in the front and 30 days in the back. See that are missing there, off both. Okay, so now let's bring this thing back this way. Okay, and let's look, the next step is seasonal decomposition, right? We need to go and look at that. Is there seasonality in here? Okay, so this is where we get a little bit complex, but it's not really too bad, okay? So you want to look at frequency, okay? Now in this case, the frequency is not 365. The frequency is what? We're looking at daily on this data, right? So you've got frequency equals 30 for daily data, and we've got MA weekly, because we're using the MA weekly, NA.omit of water data set 1 at MA weekly. And we're doing it decomp equals STL. So the first one is the time series, right? Right here. The second one is we run STL function, and the third one is we're bringing that, once it's run, we're bringing the seasonal average, or seasonal adjustment, I'm sorry, for decomp, which is this guy right here, and putting it in deseasonal count. Okay, and then we're going to plot this guy. We're not plotting this, we're plotting this. Okay, so we run this up to here. Make sure there's no errors. There's no errors. See that? Periodic, weekly, seasonal adjustment, and then we plot the decomposition. This is pretty cool. Let's do this. Boom. This shows you, is there seasonality? It removes it. Trending, remainder, what's left. It does all that for you. So now we've got the in our what? In a decomp. So that's what we call it right here, decomp. So now let's go down here and let's look at our models. We're going to start building our models off of this, right? So we're going to build an exponential model. Actually, we're going to build 2. We're going to build the regular exponential model on Holt Winters. we're going to build an ETS model, and then we're going to build an auto arima model, and later on we're going to make a custom arima model. So you'll have all 4 to compare. But let's start with this. So the exponential model is we take the deseasonalized count, which we just built right here, right? And we just put Holt winters, and you put that inside there. And it's called exponential model. We're going to put that into it right there. And then next what we do is we go to this line where we're going to forecast. I want to forecast everyone the same, so I'm going to forecast for 15 periods, right? 15 days. Remember, we're doing daily. Okay. Exponential model, comma, 15, and forecast. See that? I have forecast, and we put that into forecast 1. So forecast 1 is the exponential model. And then we're going to run it right here, right? Plot, forecast, exponential model. So let's run it and plot it. All right, so let's run this thing. There we go, and there's our plot. So now that is the exponential model. Now look carefully here. Starts at 5, ends at 35. See that? Now keep in mind that may not be ideal. It looks good, right? It looks like that really could be what it is. But let's do the same thing with some other models here. So now we have the ETS model, right? ETS of deseasonal count instead of Holt winters. And then we do the same kind of thing. We do forecast of it for 15 periods, and we do the same. It's kind of the same exact code again for the forecast and the plot part. So let's run that one and get our ETS model, right? There's our ETS model. Now look at that, from below 5, right, all the way up to 30. So that's a pretty big spread there too. Now we've done the ETS model. Now let's do the arima model, right? An auto arima model. Okay, so this gets you the optimal auto arima model right off the bat really quickly. So what we do is the same thing. Instead of ETS or the Holt winters exponential, we do auto.arima function on the deseasonalized count. We put that into auto arima 1. Let me bring this down here. Oops. And we're going to do the same forecast, 15 period, same as we did for the others. Let's do that and see what that does. Now keep in mind, this is not arima. It's going to take longer. It's got more points to pull. It does a lot more calculation in there. So give it a few seconds here while that runs. And that's running right now. See how it's not, there it is. Now it's done. Now see that? Now look at the difference. The other one started at 5 or 0. This one starts at about 10, right, to 30. And the other ones went to 35, right, and 30. So this is a smaller range here, which means it's going to be more accurate. But that's going to give you a visual perspective of that, okay? From a visual perspective, we're going to actually measure it down below here in just a second. So next, now that we've done that, let's plot all 3 models side by side for comparison. That's where this par m fro equals. So if I want to have 3 in a row side by side, I want 1, 3. If I wanted to have them up above each other going down, I'd have 3, 1. So let's take this and the same plots we just did, but let's put them together. And look what happens. Oh, that looks ugly, doesn't it? Let's bring it out so we can actually see them. There we go. Look at that. Now, when we look at that, it still needs to come out some more because it's too tall maybe. Let's bring that down a little bit. Make them look like a real graph here. There we go. It'll fix itself in a second. There we go. Now look at that. That looks pretty cool, right? So you've got 3 of them, but look at the difference. Remember I was showing you how this one's at 5 here, this one's at 5 here, and this one starts at 15, right? So this one is clearly going to be your more accurate one right here, the arima model, than these two. These have a much wider range here than this does. And that wider range means it's going to probably fall inside there, but the thing is it's not going to be very accurate. Okay, and I'll show you that with the measurements in just a second. So let's bring this back. That's really cool to see it that way. But let's bring this back and let's do the rest of this. So next, we want to plot the residuals over time to see if there's congruence or variance. Same thing, we're doing a par m fro C1, 3, which means I'm going to have 3 split up like this. But this time I'm going to do plot the forecast of the residuals, right? So let's do that. Let's see what that does. There's our residuals. Let's bring that back out again. Let's take a look at that. And what are we looking at here? Okay, we've got all 3 of them in the same row, right? Forecast 1, forecast 2, forecast 3, right? So which is which? Well, remember forecast 2 is our auto arima, right? So this is the auto arima. Forecast 1 is the Holt's Winters exponential, and forecast 3 is the ETS model, right? So if you look at that, the one that actually fits the best so far is this one and this one. From looking at residuals, this one's missing some stuff here. So let's do this. Now we've gone through that part. Now let's do the rest of it. Let's go for testing for stationarity. Now this is just for ARIMA models, right? So what we want to do is look at this right here. We want to look at the ACF, the PACF, and we want to look at that together. So we've got par M fro C 1, 2, and let's just do this right here first. Now see, you got 2 because we had 1, 2. And look at that. So by looking at that, you do have some lags over here, right? And we're going to use that in a minute here. But let's look deep, because we have those lags. Let's look a little bit deeper at it. Let's go now, because that's, see how wide this is to 60? I don't necessarily want to do that. Maybe I want to bring it down to 20 or 15 so we can really identify where those are. So let's do this. So what we've got here is you really don't, this one doesn't show it as well as this one does. This one's got our lags at a 1 and an 8, right? So we're going to use that when we do our PDQ and our ARIMA, a custom ARIMA, in a little bit here. So we've already done the auto ARIMA, right? Now let's look at this. We've got that part up. Let's look at our summary of each of these, right? So summary of, first, the exponential. The summary of an exponential is not really going to tell you something you can measure accuracy with. It's just not inside it. So that one's clearly not going to be very accurate. Let's look at the summary of the ETS model. Okay, we got some numbers here. Let's go up here a little bit. Let's take a look at this. And out of this ETS model, we've got AIC value, BIC value of about 860, and our MAPE is about 9.11. That's pretty accurate. That means we got about a 91%, 90.99% to be exact right here. Now, if we do the same thing with the ARIMA model, give me a second here. If we do the same thing with the ARIMA model, watch this. This is the auto ARIMA model. It'll give you the score, the PDQ values. In this case, you're dealing with a by score, so it's 4, 0, 0, and 0, 0, 1. So look at our MAPE here is 7.718. So what that means, that's a 92.28% accuracy on the data with the auto ARIMA. We saw it earlier. We saw that the ETS model was a little bit more accurate than the exponential model, but the ARIMA model was clearly more accurate than both. Okay, so clearly the auto ARIMA, and you can also look at it this way too. Instead of using summary, you can use accuracy, the accuracy function like this, and that just gives you this one line with your different measures. And the number one measure in there that people use is your MAPE, M-A-P-E. So what you do is you just take 100 and you subtract what the MAPE is, because that's your error, and the rest is your non-error. So that's what you'd want, and it's 7.71, which again means that you've got a 92.28% accuracy. Now let's take this and let's say, hey, you know what if we wanted to make this a little bit more accurate? What if we wanted to just make it that much better? Can we do that? And yes, we can. It's not always going to work. Sometimes the auto ARIMA is just the best you're going to get. But with this data, let's show you. So what I did was I built a custom ARIMA. So instead of using the auto ARIMA function, we used the ARIMA function. And it's ARIMA of the seasonalized count. And then we put in our order. Order is your PDQ value. So your P, your D, and your Q. Your D would be if you need a difference. Do I have seasonalities? Do I have holidays I need to difference out? I didn't really see that in there, so I'm going to put a 0 for my D in the middle. And then I remember I saw lags at 1 and 8, so I found what worked best is a 1, 0, 8. That's where those come from. Okay, now that's arbitrary. You might be able to go and switch them back and forth, or just use the 8 or the 1 and find that works better. In this case, I've already done that for you. That does not work better. The best is 1, 0, 8. Okay, so we've got that. Then the same exact code that we used before. The 15 forecast, we put in forecast 4, so we know that forecast 4 is going to be the custom ARIMA model. We've got our plot 15. And we're going to run this and plot out the custom ARIMA model. See what that looks like, okay? So let's do that. There it is. And remember, if we wanted to see it bigger, we could put a what? That par M fro right here. You could put, because we're only doing one graph, we could actually put this right here and put that right in front of the plot. And we could say 1, 1, right? That would make it so it's got one graph on there. So let's just do that. There you go. That looks a little bit better. So now when you look at that, see again, it's 15 and 30, right? So it's going to be as accurate at least as the arima model, right? Because the other ones were bigger and had more width to these, which means that they are less accurate. But this one's going to be more accurate. Now let's go and take a look at this. Now that we've built this, we've run it, let's take a look at it. Let's run accuracy. Remember I showed you you don't have to run the whole summary thing, you just run accuracy of it, the accuracy function. So let's do that of our custom arima model. See how quick and easy that was to run the custom arima? We've got 4 models here right now. Okay, and what is it? Our MAPE is almost straight 7. So what does that mean? Almost 93%. Basically, we end up with 92.99% accuracy. That's pretty darn good. Okay, so it's even better than our arima model by a little bit, by 0.7 something. Okay, so next, now that we know that this is our most accurate model, let's plot all 4 of them together like you saw at the beginning, so you can see it all together. And let's do this and bring this up a little bit right there. And so we got par m fro equals c 2 comma 2 instead of 1 comma 2, right? If we had 1 comma 2, we just see 2 graphs here. We want it so we have 4, 2, and then 2 below. And then we're going to do all the plots that we just did, plot, forecast, the exponential model, the arima model, the ETS model, and the custom arima. Okay, so let's do this all together here. Ooh, look at that. Let's bring that up and let's take a look at that. Now remember, we know that going into this, our accuracy was highest with the 2 arima models, right? So let's take a look at them. Where are they? Here it is. Because we did it right, we have it so the arima models are right on top of each other, so we can go compare them back and forth. Plus, to the left, we have the exponential Holt winners, and we have the ETS on the left. So you've got the ETS right here, you've got Holt winners right here, and you've got your forecasts for the arima models right here. Now, when you look at these, remember, look at the numbers on the left, right? So you got 15 to 30, 15 to 30, so these are your arimas, right? And look at this one, 15 to 30 will be inside of this. See how much bigger the graph goes here outside of that? That graph would be like this and this here going, like, I mean, it'd be huge compared to that. So this is less accurate. And this one is same thing, even bigger, 5 here. So it's bigger at the bottom because this one goes down more than this one goes up more. But even then, it's still much bigger. These two are much bigger than these two. So you can tell by looking at it that these two are your more accurate ones, but they're very close. They're both realistic looking, and they both look realistic with the data that's on there. Very realistic. And this one's just a little bit more accurate. It's actually like 1% more accurate. Give or take there a little bit, but it's about 1% more accurate with this one. So we go with that one. But you now have your forecast, right? You have your forecast values. You can actually see and plot your forecast. We looked at 4 different models really fast. We built them up. We tested them. We compared them in numerous ways. We even took things into consideration. Well, what if we had missing values? What if we had other things going wrong with it? And I showed you how to go and forecast the Baltimore water quality levels, and especially in particular the lead levels of their water. So you can see here, can we predict that? Yes, with very high accuracy based on their water, based on location number 1. Now, we did not look at locations 2, 3, 4, 5, 6, 7, 8, or 9, or 10, but we could have done that and it'd probably come up about the same. And the cool thing is that you could take what you built here, this model, and apply it back to that data, so it doesn't matter. You don't have to rebuild the model again. So that's kind of cool and neat. Now, while we're sitting here talking, I want to tell you something. I have a friend, his name's Mark Gingrass, and he's got a website or a video channel on YouTube very similar to this that you guys would get a lot of value from. He covers things like programming, R, all kinds of explanatory stuff, especially for people that are newbies and beginners to R and beginners to coding and stuff like that. Covers a lot of great stuff. So do me a big favor and yourselves a favor, because it's only good stuff for you to learn. Go and visit his site, take a look at it, his YouTube channel, and go look at his videos and see if you like it or not. I'm sure you will. Thanks again for watching. Please take a moment to subscribe. I need you to subscribe. If you haven't subscribed, you need to subscribe, because You're not going to know when I come out with new stuff like this. I've got a bunch of other great ones I got coming out soon too, and you're going to want to be, made aware of it. It doesn't bug the crap out of you. It'll just send you a quick little, email that says, or something like that. It says, hey, a new one's posted. You can go take a look at it. But please go subscribe, like, and share. And I hope you enjoyed this and learned a lot. I'm going to put the code from it up eventually, and I'll also post the data set for it. All right, thanks again, and have a great day.